So let's move to our next activity. Then the first invited speaker is Professor Danqi Chen. Because we only have limited time for each invited speaker, so I have to keep the introduction very short. And Danqi Chen, she's an associate professor of, she's an assistant professor of computer science at Princeton University, and she could lead the Princeton NLP group. And she's very well known at question answering. So if you have ever working on question answering, you must have heard her name. It is our pleasure to listen to her new research about representation learning. Professor Chen, now the stage is yours.
All right, can you hear me?
Yes.
Great. Okay, thanks for the introduction. So as you introduced, I'm an NLP person, so I don't really work on audio and speech. So the topic of this talk will be mostly about pre-training language models. I'm actually also really hoping that people from speech and NLP and computer vision communities can actually discuss more about these topics. So thanks for having me here today. So I feel I don't need to say more about how successful pre-trained language models are in NLP today. So today we have all these sorts of like different types of the models, such as autoregressive language models, masked language models, or even text-to-text models, such as T5. So some of these models are actually not necessarily language models anymore, but this collection of pre-trained models has been making huge impact in our field. So even after the development of the GPT-3, when more and more companies and institutions have been competing for further scaling up language models. And the one trend I have been seeing over the past 2 years is that actually many ideas can be actually shared and transferred between different modalities. For example, this is like a mask autoencoder MAE work. Basically shows that the BERT-style pre-training can be also used in learning image representations by masking a portion of the input images. And this idea has been also recently unified in this data-to-vec paper, which shows that basically the same framework can be actually used for images, speech, and also language. I also believe the author of this paper will be also speaking at the workshop today. So I actually worked at Facebook in 2019 with a robotic team. And in the past 2 years, I've been working at the university with a group of graduate students. So one key question I've been thinking over and over is that these models are actually getting bigger and bigger today. And many of these models actually require hundreds or even thousands of GPUs to finish the training. So as an academic researcher, so what can we do in this pre-training era? So today, many of our graduate students probably have access to at most like 8 GPUs. So what can we do if we only have 4 or 8 GPUs to spare? So how can we actually make this pre-training more accessible and affordable? On the other hand, I actually also believe that today we still have a lot of pre-training that needs to be accomplished. So like low resource languages or specialized domains. So can we actually really rely on this very few number of tech companies to actually finish all this pre-training work? So actually, I don't really have a clear answer to this like a very big questions yet. So in this talk, I actually would like to quickly talk about 2 case studies that we have done in the past year. So I hope that this work can actually show some problems and the limitations in the existing pre-training work. And hopefully they can also point to some promising directions for efficient pre-training. Okay, so the first work I would like to talk about today is actually an exploration of the optimal masking rates and also masking strategies in masked language models. So this work was done by my graduate students, Alex Vatik, Tianyu Gao, and Zexian Zhong. So this is actually a very recent work, and you can actually find the paper on arXiv. So everyone knows what is BERT. So one crucial design choice in BERT is that BERT always masks out 15% of input words and predicts the masked words. So where does this 15% come from? So this is actually the common belief from the author of the BERT, Jacob Devlin. So from his talk slides. So if you mask less than 15%, basically the models will actually become very expensive to train. And then if you mask too much, there isn't enough context for you to predict the masked words. So since the BERT came out, actually a few people have actually tried to change this 15% masking rate. Indeed, actually, all the follow-up models like Roberta, Spanbert, Albert, Debata, and many others mask language models, they basically always consider adopting the same 15% masking rate, no matter how big the model sizes are, or actually how sophisticated, or actually what different masking strategies these pre-trained models adopt. So these masking strategies include span masking or PMI masking. So we also know that actually masked language models actually more effective than autoregressive language models due to their bidirectionality. So if we control the model size and the corpus size, so masked language models will always become better after a small number of training steps in terms of downstream performance. But on the other hand, this 15% masking rate has been viewed as a bottleneck for sample efficiency of pre-training masked language models, because you can always only learn from 15% of tokens, given you have 100% the examples to use, but you can only learn from the 50% tokens. So this has been viewed as a limitation for masked language models. So one natural question we are actually really curious and try to answer in this work is that, can we actually try to mask more in masked language models? So why we cannot mask more in masked language models? So this recent MAE paper, they basically show that in images, if you can mask 75% to 95% portion of images, you can still reconstruct the original input plausibly. If you see the images on the left, especially for 75% or 85% masking rate, the reconstructed images actually pretty close to the original image. Can we actually do this for text? So this is actually the code from the MAE paper. And actually most people believe that the information density is actually very different between languages and images. So images have actually natural signals and have way more redundancy, but language is actually much more information dense. So in our paper, we actually uncovered quite a surprising finding, at least to me, that we can actually try to mask more, actually way more than 15%. So here is one example sentence. So the sentence is, we study high masking rates in pre-training language models. And then if we mask 50% of the input words, and the perplexity will be around 17.7. So this is just one single example, but the perplexity is actually evaluated on a very large unlabeled text corpus. So next, we are actually trying to mask 40%. And the perplexity would actually increase to 69.4. So it's actually much higher compared to 17.7. So we actually try to mask even more, try to mask 80%. So as you can see from this example, you can actually basically only see 3 words: we hide models in the basically the corrupted input. And it's actually impossible to construct the original input. We study high masking rates in pre-training language models. And the perplexity is also extremely high. So perplexity is actually as high as is already over 1,000. So here actually comes to the surprising part. So when we evaluate these 3 models on the downstream tasks, we actually find that a 40% masking rate model is actually even better than the 15% masking model. And if we consider this a downstream task like MLI or QNI or Scholar data set, and for the 80% masking model, actually the gap is actually much smaller than we anticipated. It's actually basically only 3 to 4 points drop across all these 3 tasks. We actually also evaluated on many other tasks in our paper. So just to clarify a little bit, so these results, we actually built these results on efficient pre-training recipe from this 2021 paper. So essentially we trained a very large model for only 24 hours on 8 low-end GPUs, and the performance is actually at least good as BERT-based. So I don't have time to elaborate on this pre-training recipe, so you can check out the details in the paper. So from this result, we actually hypothesized that the ability for masked language models to reconstruct the original inputs may not directly correlate with the repetitions for downstream fine-tuning. And this result is actually pretty surprising to us, and actually also could be quite different from our original understanding about how masked language modeling actually works and how much context the model actually needs to learn from. So we also actually conducted very careful studies in the paper with different pre-training recipes, including the efficient pre-training recipes and also the original robot pre-training recipe. So as you can see from this figure, so the horizontal lines in each figure are basically from the baseline 15% masking rate. So our conclusion is that the 40% masking rate is consistently better than 15% masking rate, but the improvements could be even larger if we combine the training with the efficient training recipes. And then we also have several other really interesting findings in our paper. So first, we find that the larger models actually should have the capacity to actually adopt larger masking rates. So if in the future we want to further scale up mask language models, we shouldn't use a fixed masking rate, and we should actually try to increase the masking rate, and the different size of models should actually adopt different masking rates. So we also find that increasing the masking rates, actually the most naive uniform masking could be actually equally good or even better than the sophisticated masking strategies, such as span masking or PMI masking. So this result is also a little bit counterintuitive. That means that if we tune the basically the masking rates, we should just stick to the most naive, the uniform masking. So one additional bonus is that we also find that this 80-10-10 corruption strategy might be also not that important as observed in previous work. Okay, so these are actually the most surprising or interesting findings in this work. So the most important thing is that what can we learn from these results? So we did controlled experiments, and basically we find that the less we actually corrupt the input, the better repetitions we can learn. And the more we actually can try to predict in at least in a fixed number of training steps, the better downstream performance we can get. But so far, all the existing work always use a single variable, which is the masking rate, to control the two things. So basically means that the less we corrupt, the more we can predict. So one possible question to ask as a future direction is that, can we try to disentangle the corruption rate and the prediction rate to enable more efficient pre-training? So another question you might be curious is that, why do we even care about or want this kind of high masking rate? So at least I actually believe that the high masking rates could actually lead to more efficient implementation of pre-training. If we can mask out 50% of tokens, that means that we can probably only encode unmasked tokens to reduce the number of computations. And the MAE paper actually already shows 4x speed up using only by masking 75% of the input. But this hasn't really been verified successfully in NLP yet. Okay, by the way, how many minutes do I have? 5, 6? Okay, so in the next few minutes, I'm actually just going to detour a little bit and quickly talk about another idea around contrast learning. And this work is a work we published at EMP 2021. And this work was done by my student Tianyu Gao and Xingchen Yang. So in the past 2 years, contrast learning has been highly successful in learning image repetitions. So some work like SimClear, Moco, and there are many other great work in this space. So the problem we want to study is actually here is how to learn good sentence repetitions. So given one sentence, there are 2 docs running. How can we actually learn good repetition for these sentences? And this is a very fundamental and well-studied problem in NLP. So given pre-trained repetitions have been already so powerful, so the easiest thing we can think of is actually to directly use our pre-trained language models to produce sentence embeddings, such as just taking the average of the bird hidden repetitions. However, actually, the recent work has identified one key issue in the pre-trained language models, that these pre-trained repetitions are actually highly anisotropic. So that means that the learner embeddings actually occupy a narrow cone in the vector space. And this limitation would actually greatly limit the expressiveness of these repetitions. So for this reason, several post-processing methods have been actually proposed to map these pre-trained repetitions to an isotropic space. And some work include BirdFlow in 2020 or BirdWhiting in 2021. So in this work, we actually introduced an approach called SimCSE. So SimCSE is actually a very simple contrast learning framework for learning sentence repetitions. And it has two approaches. So the first one is actually a purely unsupervised approach, and we call it unsupervised SimCSE. Essentially, this approach just uses like dropout as data augmentation to create positive pairs. And we also have a supervised model, but I'm not going to talk about it here. So this approach is essentially very, very simple. So it essentially takes a pre-trained BERT encoders and adopt the standard InfoNC contrast loss and fine-tune the BERT encoders on the unlabeled data. And the key idea behind unsupervised SimCSE is that it actually adopts using like dropout mask to do the data augmentation. So here is one example. So here we take one sentence. The two dogs are running. And we just feed the sentence into the BERT encoder twice. So we first feed the sentence into encoder, and then we get one embedding. And the next, we are going to feed the same sentence again into the encoder. And then we can create another embedding. And then we just, the only difference between these two embeddings is applying the dropout mask twice. And then we can get two embeddings. And the dropout here is just a default dropout in the BERT encoder, and we don't add any extra dropout. And for the negative example, negative pairs, we just use in-batch negatives, basically the repetitions of other sentences in the same mini batch. So this is actually very, very standard, simple formulation. And the training objective can be basically, you can see from this slide. And this is a very standard formulation of contrast learning. And really the key thing is that we try to apply the dropout to the same sentence with two different dropout masks as the positive pairs. And this approach actually works extremely well. So on the standard semantic textual similarity task, so if we compare the unsupervised SimCSE to the average of the BERT embeddings, and the previous strips are unsupervised sentence embeddings, so our unsupervised SimCSE is much, much stronger. Basically, it achieves over 10% absolute improvement on average at that time last year. And actually, a very important thing I want to highlight here is that SimCSE is actually very cheap. So it takes BERT encoders and it trains CMC on top like just 1 million sentences. And this can be actually done like on one single GPU for like just train for 1 hour with like a very small batch size of 64. Okay, I'm going to skip this slide. Basically, we also show that the repetitions that learn from SimCSE can actually indeed be actually like improve the isotrophy of the embedding space. So this is basically all I want to say about the SimCSE work. But again, the next key question is that what can we learn from this result? So in this result, I show that the basis of pre-trained BERT repetitions are actually highly anisotropic. And a very simple objective like SimCSE objective can actually contrast learning objective can actually ease this problem. So given that we know that BERT repetitions have this limitation, so the next bigger question we want to ask is how can we, if we actually fix this problem? Shall we try to fix this problem at the pre-training stage or fine-tuning stage? So in the past year, there has been actually some work showing that adding like contrast learning objective on top of our standard pre-training and fine-tuning paradigm can actually give you better downstream performance. But all this existing work, they all build on like existing pre-trained BERT repetitions. And the one question I'm actually particularly care about is whether we can actually do this kind of contrastive pre-training from the scratch for language model pre-training. Would that actually be a key solution to improving the efficiency of pre-training? Actually, I personally think this is actually very promising, but I actually don't really know the final answer yet. Okay, so this is my last slide. So I'm just going to conclude here. So going back to the question, how can we make pre-training more accessible and more affordable? So I talk about two like promising directions. One is trying to use high masking rates, and I think combining the high masking rate and efficient pre-training recipe and the implementation could actually be a promising solution to efficient pre-training. I also personally believe that contrast pre-training could also be a key to actually unlock the pre-training recipe. So I also want to emphasize that in the past 2 years, we actually got a lot of inspirations from the other research communities like computer vision and speech people. So I really feel that we need to promote more conversations like this and share more insights together. Okay, so I'll just stop here. Thank you so much. Yeah.
Thank you very much for Professor Chen's insightful talk. We will have the Q&A session after all the invited speakers.